Welcome back. In our last explainer, we really dug into the whole challenge of generalization error. Today, we're going to learn how to actually measure that error using one of the most powerful and common tools in the entire machine learning toolkit, the root mean squared error, or RMSE.
All right, here's the game plan. We'll start with why we even need a single score for accuracy in the first place. Then, we'll define what RMSE is, and, more importantly, how to interpret it. After that, we're going to dissect the very nature of error itself, and finally, see how this all leads to that crucial balancing act between bias and variance.
Okay, so you've done the hard work. You've trained a model, and it's churning out predictions. That's great. But what now? How do you go from this massive list of individual predictions to a single, clear verdict on how well it's actually performing?
I mean, you can't just sit there scrolling through thousands of different predictions, right? That's not practical. What we really need is one single, powerful number that summarizes our model's accuracy at a glance. And that number, more often than not, is the root mean squared error, the RMSE. It's one of the absolute workhorses for evaluating models, especially when you're dealing with regression tasks. So, what is it? Think of RMSE as a kind of master scorekeeper. It looks at every single time your model made a mistake, every time it was a bit too high or a bit too low, and it boils all of those individual errors down into one comprehensive score.
Now, I know this formula might look a little intimidating at first, but the name root mean squared error isn't just a fancy label, it's literally a set of instructions for how to calculate it. Let's walk through it. So for each data point, you start by calculating the error. That's just the difference between the actual value and the predicted value. Then you square each of those errors. Next, you find the mean, or the average of all those squared values. And for the final step, you take the square root of that average. See? The name tells you exactly what to do, just in reverse. Error, square, mean, root.
And this brings us to a really vital point. If you stop right before that last step, before taking the square root, you've got another key metric called the mean squared error, or MSE. So RMSE is simply the square root of MSE. This connection is going to be a really big deal in a few minutes when we start to break down why our models make mistakes.
So, we've got our RMSE score, we have a number, but what does that number actually mean? How do we read the signals it's sending us? Let's break it down.
Okay, a few key things to remember. It's never negative. And an RMSE of 0? Well, that would mean you have a perfect model. So the goal is simple. Lower is always better. And because of that final square root step, the RMSE is in the exact same units as the thing you're trying to predict. So if you're predicting prices in dollars, your RMSE is also in dollars. This means you can think of it as the typical size of your model's errors, kind of like the standard deviation of its mistakes.
Now, here's a key feature of RMSE. It hates big mistakes. Unlike mean absolute error, which treats every error equally, RMSE squares the errors. Think about that. An error of 10 gets squared to 100, but two errors of 5 only add up to 50 after they're squared. This means that one single massive blunder is going to punish your score way more than a bunch of small, acceptable errors.
So imagine you have two models. They're both pretty good on average, but one of them, just once, makes a prediction that is wildly, disastrously wrong. An outlier. That model's RMSE score is going to shoot through the roof. This is what makes RMSE the perfect metric for situations where large, costly mistakes are just not an option.
And here's a really important rule to live by. You can't compare RMSE scores across different data sets. It's totally scale dependent. An RMSE of 10 might be incredible if you're predicting house prices worth millions, but absolutely terrible if you're predicting exam scores out of 100. So remember, only use RMSE to compare different models working on the exact same problem.
But RMSE is so much more than just a grade. It's actually a diagnostic tool. By looking under the hood at its core component, that mean squared error, we can actually start to understand where our model's errors are coming from.
And this, right here, is one of the most fundamental ideas in all of machine learning. The mean squared error isn't just one thing. It can be perfectly broken down into these three distinct components, and understanding these three sources is the key to building much better models.
First up, we have bias. Think of this as the error from a model that's just too simplistic. It makes rigid assumptions and completely fails to capture the true, complex patterns in the data. We call this underfitting. It's like trying to describe a winding road using only a short, straight ruler.
On the flip side of that coin, you have variance. This is the exact opposite problem. Here, the model is too complex. It's so flexible that it doesn't just learn the underlying signal, it starts to memorize all the random noise in your training data. This is called overfitting.
And finally, we have irreducible error. This is just the inherent randomness or noise that's part of the data itself. It's the static on the line. And no matter how amazing your model is, you can never get rid of this error. It sets a theoretical lower limit on how good your predictions can ever be.
So our total error is a mix of bias, variance, and that irreducible noise. This brings us right to the central challenge, the very heart of modern machine learning, finding the right balance.
You see, building a great model is a constant balancing act. If you increase your model's complexity to reduce bias, you almost always increase its variance, and vice versa. The real goal is to find that perfect sweet spot, that one point that minimizes the total error, and that's the very error that our RMSE metric is helping us track.
So we've seen that RMSE is a powerful tool, not just for scoring our models, but for understanding this fundamental trade-off between bias and variance. Which brings us to the big question. How do we actually manage this trade-off to build better models? How do we find that sweet spot? Well, that is exactly what we are going to dive into in our next explainer. I'll see you then.